Okay, let's get started, please. So, are there any questions on what we're doing? Any questions? No? Okay. So, today we're going to finish up basically the pre-calculus review and go on to maybe the most important idea in the class. That's the notion of limit. Okay, but start off with just reviewing trigonometric functions. I'm going to start off with the following question. Where is the 360 degrees? Or rather, where does the 300, where does the 360 and 360 degrees come from? But really, I'm asking, where is it? Somebody says, oh, a circle is 360 degrees. Where is the 360? Do you see 360 somewhere in the circle, inherently in the circle? Why is this called 360? Does anyone know? What is it 360?
Something with can't you get it from radians?
From radians? Well, that's right. So there's another way of measuring the angle, called radians. But let's just think about degrees itself, right? Where does this number 3? Why isn't it say 100? We have a base 10 system. Why don't we use 100?
If you draw that, it's 180.
Okay, so why is that 180? Why is that, again, it's sort of the same question. Why is that called 180? Right? Why is the whole thing called 360? Or you could say, why is half of it called 189?
Didn't the ancient Greeks use it as some sort of rate of what it is? Or let's say all the way after the year.
So yeah, actually it is related to the, it's actually related to the year. I think to the Egyptian calendar. Yeah, I believe. But again, this is some sort of fake history that I'm going to make up because it's convenient. Along with the fake history, I'll offer you, I think what is a real myth. The ancient the Egyptians actually had 360 days in their year, and then they had five extra days, which were sort of considered outside of the year. I think. And this is where it's going to get really sketchy. There is some story about a goddess who is pregnant, and she has been because I think one of her children is foreordained to overthrow the ruler of the gods. She's forbidden to give birth within the year, and so somehow the god of time, I think. Makes 5 extra days, and on each of those days she gives birth to one of her 5 children. She's carrying 5 children, and so those are the 5 extra days. So for them, their months had 30 days and then 5 days extra to make it consistent. Okay, so that's where the 360 comes from. But so it's rather an artifact of our planet. It has nothing to do with the circle itself, right? It's an artifact of the planet, or it's an artifact of our solar system, right? If an alien came, the alien would be very confused why we have 360, right? Because maybe it has nothing to do with the circle, right? So then there's this thing. So instead of using degrees, one typically uses radians. So we will use radians. One uses radian here. Okay, and the way you define the angle. So if somebody says, how do you describe this angle? The way you describe this angle, okay, like what do we mean by radian measure? You take the unit circle, okay, and if somebody says, what do you call this angle in radians? What you do is you measure this length, okay, you measure this length thing here, and you say that the angle is angle is S radians. Okay, so what is this angle in radians? Well, you take the unit circle, that's important. Take the unit circle, and you would measure this angle, and you say we call that thing S radians. For example, what would be the full circle, the angle for the full circle? Well, you would measure this whole arc, and what's the angle of this whole thing here? What's the length? What's the perimeter, the circumference of this whole thing? 2 pi, right? 2 pi. So the whole thing is 300. The whole thing is 2 pi radians. So full circle, full circle is 2 pi radians. Okay, and in this case, the two. If somebody says, "Where's the 2 pi?" Right? Where's the 2 pi? You can answer, right? If the alien came and said, "Well, why do you call this thing 2 pi?" And we say, "Well, on the unit circle, the length that is, I think the word is subtended by the angle is the length of the arc subtended by the angle is what we call the radian measure, and so the length of the angle, the length of this arc is 2 pi. Where's the 2 pi? Here it is right here. Okay, it's not something we invented external to the circle. Right, here it is right there. Okay, so that's what you use. And then, once you have radian measured, then you can define trigonometric functions. Trigonometric sine and cosine. So, sine and cosine. So, you take the unit circle and take an angle theta. Okay, and let P of theta be the point where this ray intersects the circle, the unit circle. Okay, so P theta is this thing, and then here's how we define cosine sine. Right? Cosine of theta. Somebody says, "What's cosine of theta?" Cosine of theta is the x-coordinate of P theta, of that point P theta.
Sorry, P theta is the intersection?
P theta is this point right here. Point of intersection where the ray intersects the circle. Intersects the circle.
Wait, so theta is like the y value?
No, theta is the angle. So if somebody says, what's the cosine of pi over 2? Okay, somebody says, what's the cosine of pi over 2? What the answer would be, you take the unit circle, you take the angle pi over 2, and take the point on the unit circle that lies at that angle, and then you look at the x-coordinate, right? The cosine of pi over 2 is the x-coordinate of this point here, which we're calling p pi over 2. And what's the x-coordinate of it? 0, right? Right? If I ask you, what's the cosine? Hold on just a second. What's the cosine of 0? 0. 1, right? Because you say, well, I'll take the x-coordinate of this point, right? The cosine of 0 would be the x-coordinate of this point, right? Cosine of 0, the x-coordinate of the point that you get on the unit circle when you take a ray going at angle 0, right? So the 0, so this one is p pi over 2, this one is p0, right? If I said, what's the cosine of 3 pi over 2? What would it be? 3 pi over 2, I'd be here. Cosine is the x-coordinate, 0. Like, what's the cosine of negative pi over 2? 0, because I'm going to go back to negative pi over 2, the x coordinate is 0, right, et cetera, et cetera. Okay, so the cosine is the x coordinate. Here's how we define it, because using the unit circle. Yeah, Claire.
Just answer my question.
Using the unit circle. Here's how we define the cosine using the unit circle. The cosine of theta is the x coordinate of the point on the unit circle that you get by extending the ray from the origin at angle theta. Similarly, the sine of theta is defined to be, and this dots, these colon equal sign means is defined to be, so this is defined to be that, is defined to be the y coordinate. Okay, where d theta is the point where this bang at angle theta intersects the unit circle. Okay, so for example, what's the sine of 0? It would be 0, right? Because you want the y coordinate of the point you get when you intersect, when you draw a ray at that angle. So you draw a ray at this angle, say, what's the y coordinate you get at this point? What's the y coordinate? 0. Right? What's the y coordinate I'm sorry, what's the sine of pi? It'll also be 0, right? Because you would go this way, you get this point, the y coordinate is 0. Right? What's the y coordinate of, I'm sorry, what's the sine of, negative pi over 2, negative 1, etc., etc. Right? So you see how these functions work. Graphically, right? If we drew the sine, here's our theta, right? When theta is 0, what's the sine? When theta is 0, the sine is 0. When theta is pi over 2, the sine is 1. When theta is pi,
0.
Back to 0 again. From 3 pi over 2, negative 1, negative 1, and then at 2 pi, you're back to the beginning, so you're back to 0 again. And you see that after that it starts repeating, right? It starts repeating. You have this function. Oops. You have this function which is a periodic function. It has a period that repeats. So, of course, sine of theta equals 2 pi is sine of theta. Right? Once you pass 2 pi, then you basically start over again. Right? It has this is called, the sine is 2 pi periodic. If you want to use that language. Okay. And then the cosine, we can see the same sort of thing happens, right? This is the sine. The cosine right? You rather get something like this, right? And then it repeats. And to the left as well. Okay. Any questions so far on, particularly on how we define the cosine and the sine? I know you may have defined it using triangles before, but this is actually the more natural way to do it. So trigonometric functions we're going to define using the unit circle. So the cosine and the sine, right? To sort of right. So just made it here. Cosine theta, sine theta are the coordinates of the point where a origin at angle theta intersects the unit circle. Cosine theta, sine theta are the coordinates of the point where a ray from the origin at angle theta intersects the unit circle. Okay. And we start, there's a convention that you start measuring with this as 0, with the positive x-axis as 0, and then as you go counterclockwise, the angle becomes more positive. So that's a convention. We could have done it some other way, but everybody does this way. Okay, so some identities. Trigonometric identities. The first, cosine squared plus sine squared always equals 1. Why is that true? Why is that true? Pythagorean theorem, right? Can you give me a little bit more detail?
Well, if cosine is x and sine is y, it just ends up kind of being a squared plus b squared plus c squared.
That's right, that's right. So what we get, or maybe cleaner to say it this way, y cosine theta sine theta lie on the unit circle. Right? The unit circle, what's the unit circle? It's a set where x squared plus y squared equals 1 by the Pythagorean theorem. Right? So this thing lies on the unit circle, so it's x coordinate squared plus y squared coordinate squared must be 1, basically by the Pythagorean theorem. Right? And so this is called the Pythagorean identity. Number 2, cosine of negative theta equals cosine of theta. And similarly, sine of negative theta equals negative sine theta. Okay. Take a minute and draw a picture that convinces yourself of this fact. Right? Cosine theta and cosine negative theta, where are they? What are they? Okay, so what does the picture look like? What picture have you drawn? Yeah, Stefan.
I put a point at pi over 2.
At what?
Pi over 2.
Pi over 2? Okay,
Yeah.
so right here?
And then at negative pi over 2.
Okay.
And at both cosine of 0.
Okay. So yeah, that'll work for pi over 2. Maybe
Yeah.
instead of doing it for a specific point, just do it for some some point that you call theta. Okay, so do it for some angle theta rather than for specific theta. Choose some theta that is more general. You say, well, look, if this is theta, then this is negative theta. Right? This angle is negative theta. Right? And what you see is that they have the same x coordinate. Right? They have the same x coordinate. Right? Because you have exactly the same triangles here. Right? So this position, the x coordinate here is the x coordinate. is what you would see, that these guys have the same x coordinate. Yes? Matt?
Wouldn't that also be proven by the graph of cosine, given that it's an even function?
Yeah, it sure looks that way. It sure but I'm not gonna trust the graph because who knows if it's exactly. It sure looks like an even function, right? It looks like an even function, but maybe this is more defensible. Similarly, right? What you can make the same sort of argument for the sine, right? The sine of theta and the sine of negative theta are negatives of each other, right? As you see on the picture, right? The y, remember the sine is the y coordinate, right? So this is sine theta, and here is sine negative theta, right? The sine is the y coordinate of this point, right? The cosine, remember, was the x coordinate of this point. So here's the x coordinate, this is cosine theta, this is also cosine negative theta. Sine theta is here, sine negative theta is here, and again this is just a reflection of that triangle. You see that sine theta equals negative sine negative theta. Any questions? Should I draw it bigger? Does anyone want me to draw it bigger? Prima. Sure. Okay. So the picture is here. Right. There's an angle theta. There's negative theta. And what you see is that, right. So we are calling this thing p theta and p negative theta. This x coordinate is the cosine of theta. It's also the cosine of negative theta, right? Because right, the cosine is the x coordinate of this point. That's here, right? The sine of theta is here. The sine of negative theta is this value, and we see that they are negatives of each other. So cosine theta equals cosine negative theta. Sine of theta equals negative sine negative theta. Okay. Number 3. Sine of let's say theta plus pi over 2 equals cosine of theta. Okay. And again, take a minute and see if you can draw a picture that sort of relates to this. And maybe start off with some theta, add pi over 2 to it, and see what you can, see if you can make some geometric argument.
Well, if you think about it on the unit.
Oh, don't do it.
Sorry.
Sorry, I thought you were going to ask a question.
Oh.
Yeah, don't do it. Okay, talk to somebody next to you, please. Somebody nearby.
I think I can do it easier. Yeah, I guess I can. I was trying to show you with data that's not like yeah, that's circle drawing competition. They're like world championships and stuff. I'm like, yeah, I know. It's really intense.
Okay. Okay. Go ahead, Sarah.
Yeah.
You were first.
Oh, yeah. Well, like just the pi over 2 is the difference, I guess, if you're
Yeah.
looking at the
Right. So you have some angle.
between.
You have some angle of theta, and then you have theta plus pi over 2. Right. So there'll be this right angle added on to
Yeah.
theta. Right. So this thing here is theta plus pi over 2. Right. What's cosine theta on the picture? Where is cosine theta on this picture?
It's
Go ahead. Lauren.
You draw a line down to the x coordinate.
Draw a line down to the x coordinate, right? Right. This thing is cosine theta. Okay. What's sine of theta plus pi over 2?
The y coordinate.
Be the y coordinate of this guy. Right? So you come over here. This is sine theta plus pi over 2. Right? And why are those two the same thing? We said that they're the same thing. Why does this picture at least sort of hint that they're the same thing? Or actually implies very strongly that they're the same thing? Alpha?
Similar triangles.
Similar triangles, right? Right here, this angle is theta, right? Because this full angle is theta plus pi over 2. So if you subtract the pi over 2 here, this angle is theta, right? You've got theta plus pi over 2, that is to say pi over 2 plus theta. Is that clear? Yes. Remember, this angle is theta plus pi over 2, right? It's theta plus pi over 2. Okay. Well, this first quadrant gives you pi over 2, so this part must be theta. Right? Right. So this angle is theta, and you see then that you have similar and in fact congruent triangles, right? Because they have the same angles, and this length is 1. Right? So one of the sides is the same length. So they're congruent triangles. Right? Being congruent triangles means that this length is the same as this length, and so you see that you see that cosine theta. This length here, cosine theta, is the same thing as sine theta plus pi. So you can use this sort of argument to show that your trig identities hold in this way. Okay, any questions about this sort of thing? The main point, I think, is to get across to you that you're going to do cosines and sines using the unit circle. Okay. Not using triangles, but the cosine is the x coordinate of a point on the unit circle. The sine is the y coordinate of the point on the unit circle. So there are the other trig functions you just define in terms of these guys. Once you define sine and cosine, then of course tangent is going to be sine over cosine, cotangent is 1 with tangent, etc. So I'm not going to define them. Those are just defined after you've gotten the sine and cosine. So let me just show a couple of ththings. Calculation of values of sine and cosine. Easy angles. Okay. So, at some angles it's easy to calculate the sine and cosine. We've been only doing the ones that are at the compass points, right? But of course, you could do pi over 4, right? What's the cosine and sine of pi over 4? Yeah. How do you figure that? Pythagorean theorem, which is a Pythagorean theorem, right? So remember the cosine and cosine are the x coordinate and y coordinate, so let's figure them out, right? Here, right, you notice that since this is pi over 4, you have an isosceles triangle, right? And so this length and this length are the same, right? And so we know that cosine pi over 4 and sine pi over 4 are the same, right? And further, by the Pythagorean theorem, we know that whatever they are, a squared, if we call them a squared plus a squared equals 1, right? In other words, a squared is 1/2. Right? In other words, a is the square root of 2 over 2. So we see it's square root of 2 over 2, square root of 1 over 2, 1 over 2. Okay, yes, fine.
So how do you know it's an isosceles triangle?
Because this is pi over 4,
Uh-huh.
right? This is, I mean, if you use degrees, this is 90, this is 45. This is also going to be 45.
Okay.
It's pi over 2, pi over 4, this is going to be pi over 4. Because you have to add up to pi. Okay. So, right, doing it for pi over 4 is easy. Pi over 6 is another easy one. Right, pi over 6. Something like this. Okay. So again, these coordinates are going to cosine, sine. What? Does anyone know them?
Isn't that sine 1/2 cosine pi over 3 over 2?
So there would be a root 3 over 2 and a half, yeah. Right, root 3 over 2 and a half. And here we'll see why. Okay, here's a funny way to see why. What you do is you take two copies of the same triangle and just flip the triangle over. So you draw a perpendicular down, make a right triangle, and flip that triangle over, and you get the same right triangle flipped over here. Okay. Well then, this is pi over 6 and this is pi over 6. So this is pi over 3, right? This angle is pi over 3. Right? What about these angles?
Also,
They're also going to be pi over 3, right? Because they're the same. They're the same angle, right? They're the same angle because we just reflected it, right? They're the same angle, and all three angles have to add up to pi, right? So you've got pi over 3, and two other things which, when added to pi over 3, give you pi, right? Two identical things which, when added to pi over 3, give you pi. So they must both also be pi over 3, right? So this is going to be pi over 3. This is going to be pi over 3. Is that good? Right. You've got pi. You already have pi over 3 here. Right. You have 60 degrees. Okay. You have 60 degrees here, right? And then you have two identical angles left in your triangle. Well, the two identical angles must add up to 120, and so these must both also be 60. Okay. So what does that give you? That gives you everything. Right, this is length 1. So this is an equilateral triangle now, right? Now we know this is an equilateral triangle, and so this length must be a half. Right? This length must be a half, right? And we know that this length, a squared plus b squared equals c squared. A squared plus half squared must equal to 1, right? And so a must be the square root of 3/4. Let's just say the square root of 3 over 2. Okay, so that tells us that this thing is square root of 3 over 2. Right. And then, any questions on that? Any questions on that? And then the last one is you just get from the previous one, like pi over 6. If this is pi over 6, then okay, pi over 3. If this is pi over 3, then this is pi over 6. Right? If this is pi over 3 here, then this is pi over 6. Right? And what we see is that then we have the same triangle here, just reflected. Right? We have the same triangle that we had over here, just reflected over here. And so the coordinates are going to be 1/2 root 3 over 2. And so those are cosine pi over 3, sine pi over 3. We're looking for the x and y coordinates of this point, and we recognize that this triangle is just a reflection of the last triangle that we're looking at. Okay? It's just a reflection of this triangle. Okay? This angle is pi over 3, and if we flip this thing, then we get that. So here are how you. Any questions about the last one? Maybe I want to look quickly. Emma? Yeah? Okay, so here are, when you're in high school, you learn a bunch of angles. And why do we like those angles? The reason is that their cosines and sines are easy to calculate. So they're just convenient. They're easy to get. Okay, so let's go on. That's the end of your pre-calculus review. Now, let's go on to chapter 2. Okay, so chapter 2, section 1, the concept of the limit. So I'm actually just going to talk a lot. So the notion of limit is actually the idea of calculus. Okay? It's basically the idea that separates calculus from all previous knowledge. Okay? I've said in other classes that I taught, I've said that calculus is basically one idea. It's that one studies to study the unknowns, to study is sort of like the motto of calculus, to study the unknown, take the limit of the known. Okay, so those of you who have seen some calculus before, somebody says, what is the area under a curve? And the answer is it's very hard to get the area under a curve, right? But so that's an unknown. But one thing that is known to you is how to get areas of rectangles, right? You know how to take areas of rectangles. So you start by taking some very coarse rectangles. You say, I'm going to take this rectangle. I don't know the answer to your question regarding the area here, right? The area under the curve, but I do know the area of these three rectangles added together, right? That's something I can do, right? And then what you do in calculus is you take the limit of that. So you start doing that. You start taking more and more rectangles. Right. And you let the partition at the bottom become infinitely fine. Right. You let the partition become infinitely fine. So you head off towards infinity somehow. You take the limit. You take the limit of that of this, and that thing you get at the end is what you're going to call the area. Is the area under the curve. So that's one thing. The other, notion of derivative also is exactly the sort of thing. Anyway, so so the notion of limit is really the distinguishing bit of the distinguishing concept that makes calculus different from everything else. This notion was foreshadowed by some work of Archimedes, something called Archimedes' method of exhaustion. He basically had something similar. It was used, by Newton, and then it was made precise, made rigorous in the late 19th century by Weierstrass. Okay, so that is the notion of limit. So foreshadowed by Archimedes. It's used by Newton, and made rigorous by Weierstrass in the late 19th century. Okay. Before then, it's sort of a shady thing. It was so shady that people of Newton's time rejected it. They said, it's just mysticism. You're dealing with infinitely small quantities. It was rejected by some philosophers. It is, I'd say, the most sophisticated idea you're going to encounter in this course. So if I were you, I'd take a look at the next section before the next class and try and get some grasp of it. If you get this idea down, then basically everything else will be a lot easier. Okay, so work very hard now to get this idea. It's crucial. Okay. And in some sense, it's a very simple idea, but it's not at all a trivial idea. Okay. So in this section 2.1, this is what the authors try to do is give you some sense of what the limit is, but they're not going to tell you exactly what it is. Okay. They're just going to give you some sort of touchy-feely idea of what the limit is. And then in this section afterwards, we'll start being more precise about it. So let's get to this thing. So informally, should I start? No, sorry. So instead of starting it, we'll start the next class. I'm going to ask you a bunch of questions. Okay, so here's genies and pool balls. So there's a bunch of genies. There's an infinite number of genies. There's also an infinite number of pool balls, each numbered with a number. 1, 2, 3, 4, 5, blah, blah, blah. Okay. And the clock, there's a clock, it's ticking in the last minute towards midnight. Okay. We've got 1 minute left till midnight, and there are all these genies, and infinite number of genies, infinite number of pool balls. Okay. So the first set of genies do the following. They, each of them, at 1/n minutes to midnight, the genies put in a ball number n. Each of them. Okay. So at half a minute, at 1 minute to midnight, they put in the first ball. At half a minute, they put in the second ball. At a third minute to midnight, they put in the third ball. At a quarter minute to midnight, they put in the fourth ball, etc., etc. Okay. So well, what happens to the band? Of course, the bag, once midnight, when midnight comes, there's all the pool balls in the band. You've got an infinite number of balls in the band. Okay, suppose they do this. At that, they put the ball into the bag and take it out. And they take it out. And then midnight comes. How many balls are in the bag? 0 balls. Okay. Suppose they do this. They, at this point, now there's a bunch of other genies. At 1 over n minutes to midnight, they put in ball n, and they remove the previous ball. Okay. They remove the previous ball. Okay, so one guy puts in the ball, the next one puts in his ball but removes the previous ball. Okay. And midnight comes around, how many balls are in the bag? 1? 0? What? 2? Okay. Who says there's one ball in the bag? What ball is it? Who says there's 0 balls in the
The
bag?
last one that was
What? The last one that was put. Well, there is no last one. Right? There's no last ball. That's good. Yes.
Is infinity odd or even?
Is infinity odd or even? There is no number infinity. How many balls are in the bag? A lot of you said 1. I'd like to know, can you tell me the number of that ball in the bag? No. These balls all have numbers on them. 1, 2, 3, 4, 5, blah, blah, blah. There's no ball named infinity. There's an infinite number of balls, but there's no ball at the end called infinity with a sideways 8 on it, except for the 8 ball, which is kind of sideways.
So you're never gonna actually get to midnight.
Yeah, 'cause
so-
they-
You never get to midnight. What
Yeah.
happened?
Because it's always going to be infinitely dividing faster. So.
Yeah.
But the clock keeps on ticking, right? The clock keeps on. It's not that the time doesn't change. Time doesn't slow down.
They just are really fast.
Are you telling me that
Their time does.
that time isn't that clock is gonna stop ticking somehow?
No, but like the genies are never going to stop.
The genies are not gonna stop.
Because they're always like,
You can always have a
smaller
smaller
amount
number.
of time before midnight that they're still like doing this.
Yeah, but there's no limit to like the smallest number we can have.
Okay, more of this next time.
Yeah.